Okay, so welcome to the 8th video in the Discrete Structures series, and we'll be continuing this series with a discussion on fuzzy sets. And this appears here in the context of membership functions. So this is kind of a continuation of the functions lecture from our last video. And once we talk about fuzzy sets, whatever these things are, we'll be looking into some operations that are possible on these fuzzy sets. So to introduce you to these topics, let me consider a couple of sets here. So let's say a set of tall people, if that even makes sense, or a set of red apples for that matter. Okay, so let me put some regular sets in here, and spoiler alert, these are fuzzy sets. So I'll put in a set of natural numbers, maybe 1, 2, 3, and so on. And let's consider this set of even numbers, right? So all those x's, which when divided by 2, produce a remainder of 0. So what is different between these two sets? The concept of well-defined comes into play. If we look into these sets, it's clear whether or not an element belongs to the set. This is a set of natural numbers. If you are given any number or any item, you can tell whether or not that would belong into this set. So if I'm given a 3.5, I can tell it doesn't belong here because the only requirement is I want whole numbers that are greater than 0 and don't have a fractional part, right? And as long as those 3 checkboxes are met, I could be sure that a number would belong in here. And similarly, I could do the same for this set. If you give me any even number, I could test against this rule to verify whether or not that element would belong. So let's say 5 would not leave a remainder of 0 and would not be in the set of even numbers, for example. And this has implications to the idea of a Venn diagram. So when we consider a Venn diagram, we are considering this border, right? So we are considering the fact that an element either has to be outside of this border, somewhere over here, or it could be somewhere inside of the border, somewhere over here. And let's say there are many things that are inside. There is no priority of one thing over another, right? So this is as much a member of this set as this is. If we come to these sets over here, I cannot make a similar distinction, right? There's no way to tell if someone is tall because it's not an objective thing to say. Some people might find somebody tall and some people might find the same person not too tall per se. And that's the same thing with red apples. I might argue that an apple is red, but you might see it kind of orange, right? So that might happen. But it's not like these things don't exist. I have seen red apples in my life and I have seen, videos about tall people on YouTube. So these things really exist. So is the idea of collecting these things, at all invalid? And it turns out that representing these kind of things as being member of a certain set makes a lot of sense. The only problem is that we cannot tell for sure whether or not a member would belong into the set, but we can only be relatively sure, right? The distinction is fuzzy. So the idea to be able to represent these things are to be able to assign a membership degree. So it is denoted by this symbol mu. And for any element, let's say A, we want to assign it a value between 0 and 1, and that kind of tells how much this value A is a member of my set. So let us define these a little bit more formally as membership functions. So a membership function can be defined as a function which assigns each potential member of a set a membership degree between 0 and 1. And the way we choose to assign these values depends very much on the use case. So let me show you a few common patterns. So let's say I have a line that represents a distribution of all the potential members that could go into my set. And for some rigor, let's just consider these are numbers, right? So let me just make a full kind of axis here. But the idea is that this horizontal axis represents all those values that could be potentially members of my set. So let's say these values are spread like so. Why not make them just discrete for this discussion? So a membership function could look something like this. So in this function, the values that are close to 0 are considered really good members. So let's say this is 1 and this is obviously 0. So nothing is a perfect member as you can see in this graph, but as values get close to 0, they are better and better members. Let me draw another model here and let me represent all possible numbers in the input space for this one. And let me consider this kind of fuzzy distribution. Let's say here's 1. Again, so nothing is a perfect member here as well. So you can see this function has a similar effect to this, but the degree of membership rises sharply on this one, while it tapers off and everything is a member, right? But as we go farther and farther, the degree gets smaller and smaller. So kind of the same nature, but this works on a finite context, but this works on an infinite context. Another one could be a square-based distribution, and this is an important one because this reflects our normal set. So let's say there are elements like such, and this is the distribution. What does this mean? All the members are equally the members of the set, right? So there is no real distinction and there is no sense of one member being more or less than the other. So these membership functions and diagrams help us to visualize different kinds of fuzzy sets. And it might still feel like this is not the most important thing to learn, but fuzzy sets have their applications in almost all of artificial intelligence and a lot of physics. It's not within the scope of our course to go into those topics, so we'll just leave the concept of fuzzy sets here and dive into the different operations possible on fuzzy sets next. So operation on fuzzy sets. Operations on fuzzy sets. Okay, so consider a fuzzy set of red apples, like in our previous example. A set of red apples. And there is one apple, and I think this apple is, let's say, 70% red. So I'm assigning a membership function of 0.7 to this apple in the set of red things. And you might think that it's only 50% red. And given membership functions like these, we want to know how we want to compute the union, intersection, and all those set operations that we had. So first we come into union. So see, this membership function, let's say this is mu1, says this is 70% red, right? That's the likelihood. And this membership function says 50%. So if I want to take the union, what should I really do? I should take the bigger of the two because this function is 50% confident, this function is 70% confident, and when I unify them, the 70% wins over. Therefore, we can say the union, the membership function denoting the union, is gonna be the maximum value between the membership degree of A and the membership degree of B taken individually. Similarly, if I talk about the intersection of fuzzy sets, so what is the intersection of these two membership functions? So when I'm taking an intersection, I really should take the minimum because in this case, the minimum confidence is within the intersection of both membership functions. Even if this is 0.7, it's at least 0.5. So that is what would be in the intersection. So I could say that the membership function denoting the intersection is the minimum of the individual ones. And then we can also look at the idea of complements. And this one should come quite simply. If you feel that something is 70% red, how much would you feel it's not red, right? It's obviously 100% minus that value. In our case, it's a range between 0 and 1. So a complement of a fuzzy set would just be 1 minus the original value of the membership function. Okay, now let us look at one example that demonstrates why the idea of fuzzy sets is so powerful. So let me consider this table. And I want to fill this up like I would do a two-variable Boolean algebra truth table. So 0, 0 here, 0, 1, 1, 0, and 1, 1. And in order to demonstrate the idea of fuzziness, let's also introduce a few more values. Let's say 0.2 and 0.5. And two equal ones. Okay, and if this is my input A, this is my input B, and I want to see what the union is, and I want to see the intersection. So according to the fuzzy set rules that we learned about earlier, the union would just be the maximum value. So this would just be 0. Here the maximum is, this gives a 1, and this gives a 1 as well. And for these two values, I have 0.5 here, 0.3. And if I take the intersection, and the fuzzy set logic asks me to take the minimum, I get a 0 here, 0 here, 0 here, and a 1 here. And lastly, for these values, I'd get the minimum this and this. And I want to ask you if this segment rings a bell. Because this looks a whole lot like A or B from Boolean algebra, and this looks a whole lot like A and B, right? Because this is a direct result of an OR operation, and this is the result of an AND operation. So really, what fuzzy sets are, they are concepts that even supersede the concept of Boolean mathematics, right? Because the idea of these maximums and minimums is giving direct birth to different logic functions, as you can see here. And I hope that provides you some good insights about fuzzy sets. This will be the end of this segment and the video. And in the next segment, we'll be starting from sequences and summations. I'm having a lot of fun making these videos, so I hope you guys are having fun watching it. So I'll see you guys in the next one. Bye.